Hello, class. This is Mr. Hart, and this podcast we want to start the physics unit of our class, which starts with motion and force. And physics is kind of fun because we start to look at a lot of things that we see every day. Things like force and motion is pretty common. It's something that is part of your daily life. So it's interesting to start analyzing some of these features, okay, and some of these things that you might think are intuitive, but really have some cool laws and principles associated with them. Okay, so let's just dive right into it. Let's start with a couple of terms that we have to be able to understand. Okay, let's start with a little story. Let's say we have this guy right here, and he works at the factory. So he takes his little motorcycle or whatever that is around to the factory, and he has to take this curved path to get there, right? You can't just travel in a straight line. And so that curved path he takes is what we call the distance, right? The distance that he traveled to get to work. Okay, that is different than his displacement. His displacement is just the start to finish distance, or in other words, the straight line distance between his house and the factory. Okay, whereas the crow flies, or whatever phrase you want to use for it, right? It's just the distance from the start to the finish is the displacement. Okay, so this curved path distance, the straight line is the displacement. Okay, so we can think about it like this. Okay, the distance is the total length of the path traveled, whereas the displacement is the length between the start and the finish of a path. Okay? And generally speaking, the distance is going to be longer than the displacement, right? Because you have to go longer distance, right? You have to take curves and go around different paths rather than just going in a straight line like in displacement. Okay? So you might be thinking, well, why do we need to know this? Well, it turns out we need to be able to kind of differentiate between the two when we talk about other terms later on, okay, or other things. Okay, it's important to understand the difference between the distance and the displacement. Okay, let's try a simple problem. Let's say we have this guy here, and he is driving down this road, okay, and he goes from 0 meters all the way down to 10 meters, okay, and then he decides he needs to go back and grab something really quick, so he goes back to 5 meters and grabs what he needs. Okay. Well, in this case, the total distance he traveled is he went from 0 meters all the way down to 10 meters, and then he came back to 5 meters. Okay. So he went down 10, back 5. That's 10 plus 5, which is 15. Sorry, 15 meters. Okay. So he went 10 plus 5, which is 15 meters. Okay. That's his distance. However, if we look at his displacement, we just need to know where he started and where he finished. Well, he started at 0, he ended at 5. That's a total displacement of 5 meters. Okay? And so this is just a simple example, right? But we can see that the distance and the displacement are going to be different in most cases. Okay? So that's some simple terms to start with. Let's look at some more complex ones. Okay? So let's go back to our guy on the motorcycle going to the factory. Okay, there's two more terms that we want to look at. There's speed and velocity. Now you may be familiar with speed, how fast someone is moving, and velocity is very related to it. However, speed is associated with this distance, and velocity is associated with the displacement. Okay, so the speed, or how fast someone's going, is the distance over the time, right? The distance they traveled over how long it took them to do it. Okay, so you might have gone 5 meters in 2 seconds. Okay, whereas the velocity is the displacement over time. So it's that straight line path again. That it's just how long it took you to go that displacement over that time. So they may only displace 3 meters in 2 seconds. Okay, so again, your average speed is going to be higher generally than your average velocity. Okay. And another way you could write it is as an equation, right? The speed equals the distance over the time, and the velocity equals the displacement over the time. Okay. Then in class, we watched this video that I narrated for college, okay, about Usain Bolt running the 200-meter. And in that video, we saw that his speed is much faster than his velocity because he's going around this curved path. Okay, so I recommend watching that. Let's do another example problem really quickly. Okay, so same guy, he goes down to 10 meters, okay, whips around, comes back to 5 meters. Again, last problem we already determined that his distance was 15 meters and his displacement was 5 meters. Okay, well, let's say it took him 3 seconds to go this distance. Okay, actually, let's do a different number. Let's say it took him 15 seconds. Okay, so if it took him 15 seconds to go 10 meters and then back, okay, then his speed is going to be his distance over his time, right? Well, his distance was 15, and his time was 15 seconds. Okay, so his speed's going to be 1 meter per second. Okay, so that's how fast he's going. He's going 1 meter every second. Now let's look at his velocity. So his velocity is dependent on the displacement. Okay, so it's his displacement over time. Okay, so in this case, it's not going to be 15. It's going to be 5 over 15 seconds. His total displacement was 5 meters over 15 seconds. Okay, so he went 5 meters over 15 seconds. That's a total of 1/3, or in other words, 1 meter every 3 seconds. Okay, so his average speed was 1 meter per second, but his average velocity is only 1/3 of a meter per second. Okay, so there again, we can see that the difference between the two of what we're looking at and what we're calculating. Okay, there's one more term I want you to know and understand, and that is a change in speed. Okay, so if you think about these Olympic runners, if you've ever seen them at the starting blocks, and when they just come out of the blocks, they are just booking it, right? They just burst out with a huge amount of speed, okay? But we want to think about how fast they're running compared to how fast they were going when they started, right? They went from 0 to 20 meters per second or however fast they're running in a very short amount of time, right? Whereas, I think about a car, it will get to as fast as these guys are going, but it usually takes a lot longer, okay? So we need something to associate with the change in speed, okay? Because a car and this Olympic runner can obviously go the same speed, but these guys can get out of the blocks a lot faster. So we want to look at that change in speed. And the term we use for that is the acceleration, okay? And what acceleration means is it's the speed change or the change in speed over time. So for example, let's say those Olympic runners, they go from, 0 to 12 meters per second, okay, in only, 1 second, okay, then their total change in speed over their time, or in other words, their acceleration is 12, okay, meters per second per second. Okay, and a lot of people say, well, that's kind of weird. You have a second over a second. Okay, well, you got to think about it. They went 12 meters per second, right? They changed their speed by 12 meters per second every second. Okay, sometimes you'll see this written out as meters per second squared. That's kind of the unit for acceleration. But just think of it as meters per second, right? They're changing their speed by 12 meters per second every second. Okay. So hopefully that makes sense. It may take a while for that to kind of sink in, but once you get used to it, it makes a lot of sense. Okay. But again, this is how we differentiate between a crappy car and a really nice car, right? The really crappy car and the really nice car will go the same speeds, right? They can both go on the freeway and go really fast, but the crappy car is going to take a long time to accelerate, and the nice car is going to take a very short time to accelerate. Okay. So that's the difference. Okay, let's try one example problem really quick. Okay, so a sports car goes from 0 to 30 meters per second in 5 seconds. What's the acceleration? Well, the change in speed from 0 to 30 is just 30, right? So we know the acceleration. I'll just abbreviate it here as accel. So the acceleration equals 30, right? The change from speed was 0 to 30, so the total change is 30 over the time it took. Okay. So that's 30 over 5, which is going to give us 6, again, meters per second, or in other words, 6 meters per second squared. Okay? Well, that's all we want to cover for this video. Hopefully that makes sense. If you have any questions, let me know, and thank you for watching.